We'll do another problem on calculating equilibrium things. This time it's partial pressures instead of concentrations, but it's the same thing. We are given here the Kp, so the equilibrium constant in terms of pressure, and so we can make an ice table and find the equilibrium pressures using the same process we did for the concentrations. So we have this reaction, and it says a reaction mixture at 25 degrees Celsius initially contains both reactants, each with a partial pressure of 0.150 atmospheres and no product. Find the equilibrium pressures of all three substances. So we're going to make an ice table, and we need to list at the top of that our reactants and products, and so generally it's might as well just put the whole equation in there because coefficients are important. So initial, these are the initial concentrations, or here are the initial pressures. So it says each reactant has a pressure of 0.150 atmospheres. And it says there's no product, so that's initially 0. Then we're going to have a row that's the change. So obviously this reaction can only go in the forward direction. So we're going to lose reactants and gain products. I'm going to make X be related to the I2. It'll also be to the Cl2. Something with a coefficient of 1 makes everything simpler. So then the change for I2 is minus X, the change for Cl2 is minus X. And what's the change for the ICl? Plus 2X. Because of this coefficient. 1 iodine will give you 2 of these. So then for the equilibrium concentrations or equilibrium pressures, we just add those 2 columns. And I'm going to put parentheses around those just because they're running into each other and I don't want them to get lost. And then this one's just going to be 2x. So we set up our equilibrium expression. Kp is equal to the partial pressure of ICl squared divided by the partial pressure of I2 times the partial pressure of Cl2. Everybody okay with that? It's the same as concentrations, we're just doing pressures instead. So we're given what Kp is, so I'm going to put that in 81.9. And my pressure for ICl is 2x, and it's that whole thing squared. It's important that the 2 gets squared as well. And then the denominator is the pressure of each reactant. So I've got 0.150 minus x times 0.150 minus x. Now you could rewrite that as that quantity squared. So we could use the solver on this one, but I'm realizing if we rewrite that as I just mentioned, we could actually simplify this and solve this one pretty easily. So I have the numerator squared and the denominator squared. Nothing weird going on. If I take the square root of both sides, then I can get rid of those. So the square root of 81.9 is going to be equal to 2x divided by 0.150 minus x. Now that's not a quadratic, so that could be solved, right? So I've got 0.15 times the square root of 81.9. I'm not saying that it's nice, but it can be done. Rearranging this, I'm going to get 1357 minus 9.05x being equal to 2x. Multiply. Then I don't know what happened in my brain. I'm back now. Add the 9.05 on both sides, 1.357. It's going to give you 11.05 times x. X then equals 1.357 divided by 11.05. 0.123. Now, just because I don't necessarily trust my algebra there, I'm going to type this into my solver. So,
That's what I got.
is it right?
Yeah.
Okay, thanks. So, this one you could do either way. My feeling is, once you get comfortable with your calculator's solver, even though this one can be solved without using the quadratic equation or anything crazy like that, it's faster to let your calculator do it, right? Because the point of this is not to practice your algebra. The point is to find out what is x. So go ahead and use the solver, and we'll practice some of that in lab today. So I have x. We're supposed to give the equilibrium pressures of all three substances. So we need to plug x into these expressions down here. So I2 and Cl2 are going to have the same pressure. I'll put it in here. So Pi2 is going to be equal to PCl2, and that's going to be equal to 0.150 minus 0.123. .027. And the unit there is atmospheres. And then the pressure for the ICL is equal to 2 times x, so 2 times 0.123. So I think that's 0.246 atmospheres. Any questions? The essential part of all of these problems is this ice table. That's where we can see this is what I'm starting with, this is how things are changing, this is how things end up. And there's variations. Sometimes we're given an equilibrium concentration and we're calculating K. We still need the ice table so that we can figure out what's going on. When we're doing this, those pressures have to all be in atmospheres, or things are going to be screwed up. If we're doing concentrations, it has to be in moles per liter. So let's talk about simplifying approximations. So sometimes we can make an approximation that makes the problem much easier to solve and doesn't really affect the accuracy of the result. So if K is very small, that means the reaction does not proceed very far to the right. And when the initial reactant concentrations are significant, we can assume that X is small in comparison and that subtracting X from the initial concentration doesn't really make much difference. Okay, so this is like you've got a load of oranges. I live in Wrigley. you get this big truck of oranges, and you go to the public scales and you weigh it, and then the guy's hungry, the driver's hungry, and so he takes 2 off of the truck to eat. Taking two oranges out of a semi-load of oranges, does that matter? Does that significantly affect the mass of the truck? No, it doesn't matter at all. Does it make a difference to the driver who was hungry and he's eating 2 oranges? Makes a big difference to him. Okay? So when we're subtracting x, sometimes we can predict that x is going to be so small in comparison to what we're subtracting it from that it is insignificant. And that's called the x is small approximation. Of course, we can't just make this assumption and not check at the end. When we are wanting to do this, we can look at a comparison. We check the assumption by comparing the calculated value of x to the number it was subtracted from. So whatever x you end up with, compare it to anything it was being subtracted from, and it should be 5% or less of what it's subtracted from for the approximation to be valid. If it's larger than that, then making this assumption is going to mess up the result. So we'll illustrate that. So consider this reaction. A goes to 2b, and here we have our equilibrium constant is 3.3 times 10 to the minus 5. So this is a pretty small constant here. Our initial concentration of A is 1 molar and B is 0. And so we can anticipate for the change that this will decrease by x and that will increase by 2x. And so at equilibrium we have 1 minus x and 2x. And so what we've been doing is we say, well, equilibrium constant is equal to b squared over a. So in this case, that's going to be the quantity 2x squared divided by 1 minus x. So we look at this equilibrium constant, it's very small, meaning the reaction is not going to go very far to the right. We're anticipating that x is going to be small enough that it doesn't really matter. So this is like the driver taking the oranges, and it makes a difference to him because there was nothing here. And now we're adding a little bit, and that's important. But the whole truck here losing a tiny bit doesn't matter. So when we do the x is small approximation, we say, well, 1 minus x, that's essentially 1. It's not going to make any difference. So we're going to assume that 1.0 minus x is approximately equal to 1.0. So now we can write out that expression. We've got k is 3.3 times 10 to the minus 5. That's equal to 2x squared divided by 1. Well, that's easier to solve, right? So we're going to find that x is equal to the square root of 3.3 times 10 to the minus 5. Divided by 2. That's inside. No, it's not inside. I'll bring for it there. It's outside. You take the square root, you get the square root of k is equal to 2x squared. 2x, and then you divide by 2. We're not assuming that x is 1, we're assuming that x is small. So here, if x is 0.000001, and I'm subtracting it from 1.0, it's not going to matter, right? Yeah, that's the idea. So we end up with the square root of 3.3 times 10 to the minus 5, and that's divided by 2. So I'm getting 0.00287, Anybody else? I can double check that and multiply by 2 and then square that. And I get 3.3 times 10 minus 5, so that's good. So we can see that x is small compared to 1. To check that assumption, we want this to be 5% or less of what we're subtracting it from. So I'm going to take this 0.00287, divide it by the 1.0, multiply by 100 to get percentage. 0.00287 divided by 1, right, times 100, that's 0.287%. So that is smaller than 5%. Assumption is valid. So I haven't quite answered the question yet, though. I just figured out what x was. I'm supposed to find the equilibrium concentrations. Well, if x is 0.00287, then what's A? Is 1.00287, which is going to end up being 1, right? Because this is only two significant figures. There's uncertainty in this tenths place, and when I subtract something that is in the thousandths place, that's within the uncertainty of the measurement. Doesn't matter at all. So we're going to say the equilibrium concentration of A is the same. And the equilibrium concentration of B is equal to 2x. So it's 0.00287 times 2, which is 0.00574, or 57. Now, we're not saying that the concentration of A did not change at all. We're just saying that it changed so little that it doesn't matter. Everybody okay with that? It makes the calculation a lot simpler. So let's do one with, like real stuff instead of A's and B's. So here we have the decomposition of hydrogen disulfide. And the reaction mixture contains 0.1 molar of one of the reactants and one of the products, and none of the sulfur initially. Find the equilibrium concentration of the sulfur. So we need a nice table. So I'm going to write the equation up at the top. 2H2S in equilibrium with 2H2 plus S2. Initial concentrations for the H2S is 0.100 molar, and for the hydrogen it's 0.100 molar, and for the sulfur it's 0. It's helpful to actually draw lines. I've got a sort of hidden graph paper on my slide, so that's why I'm able to write in straight lines. But I'll draw these lines for you because on paper it's kind of hard. So next we want to look at the change. What should I pick for the thing that's changing by x? S2. I want to pick this one because then I can just use the coefficients to describe the changes of the other ones instead of trying to do fractions or do weird stuff in my head. So I'm going to say that S2 is going to change by x. Is it going up or down? It's going up because you can't go anywhere but up from 0, right? So if this is increasing by x, then what's happening to the H2? It's increasing by 2x. And what's happening to the H2S? Decreasing by 2x. Okay? This is our dividing line between reactants and products. All the products have to either increase or decrease, and all the reactants have to do the opposite. You can't have one product increasing and another decreasing. Not possible. So then at the bottom here, we've got our equilibrium relationship. So 0.100 minus 2x. And here I have 0.100 plus 2x. And for that one, I've just got x. Let's write the equilibrium constant expression. K is equal to concentrations of the products, so H2 squared and S2, divided by the concentration of the reactant, and that one's squared because it also has a coefficient of 2. So we can plug those things in and use the solver and find out what x is. Well, what if you don't have a calculator that will do that for you? Well, you can use the x's small approximation here. This rate constant is very small, and so that tells us that this reaction is going to favor the reactants, right? When this change occurs, the reaction is going forward. And so these x's here are going to be small. This x is also going to be small. We're subtracting it from 0.1. So with the x's small approximation, wherever you're adding or subtracting x, you can say, well, it's approximately 0. I should have left some room down here. I'll make room down here. So for the approximation, we're saying that this is approximately 0.10 at equilibrium, and this is approximately 0.10 at equilibrium, and this is x. We're saying x is so small that even when I double it, when I add it to 0.1, it's not going to make any difference. Or when I double it and subtract it from 0.1, it doesn't make any difference. So my equilibrium constant, 1.67 times 10 to the minus 7, is equal to H2, so that's 0.100 squared, times the concentration of S2, which is x, divided by the concentration of the H2S squared. Well, that makes the math really easy, right? These two cancel out. And I'm left with x is equal to 1.67 times 10 to the minus 7. Is that small in comparison to 0.1? Heck yeah. You can double check. 1.67 times 10 to the minus 7 divided by 0.1 times 100. That's like 1.67 times 10 to the minus 6%. Somebody want to do that? That's a lot less than 5. So this reaction does happen, but it only goes a little bit. We do have a concentration now of S2. S2 concentration at equilibrium is x, and so our answer, S2 concentration, is equal to 1.67 times 10 to the minus 7 molar. There. Any questions? One of the things that we kind of gloss over or lie to you about in Chem 1A is that all reactions, almost all reactions, there's some of reactants and products present at equilibrium. It might be a teeny tiny amount. And we'll talk later about solubility, and we use silver chloride as an example a lot. Silver chloride is insoluble in water. Does that mean that no ions dissolve in the water? No, some do. Because if 5 ions dissolved, well, that's 5 ions, right? That's a crazy low concentration, and so for all practical purposes it's 0, but it isn't actually 0. Okay, so here is the same reaction, and we're just starting with different concentrations. So let's just try to run through this fairly quickly. Still going to make a nice table. So initial, the H2S is 1.0 times, well, it's 0, 0. 1.00 times 10 to the minus 4. The H2 is 0, and the S2 is 0. So again, I want to call the change in S2 X. So here, this is the dividing line between the reactants and products. I'm going to say that S2 is going to change by plus X, H2 is going to change by plus 2X, and the reactant is going to decrease by 2X. Okay? And then the equilibrium, we've got 1.00 times 10 to the minus 4 minus 2X. We have 2X and we have X. So again, we have a situation where our equilibrium constant is small. So we can approximate X is small, X not being significant when we subtract it from that number. So the X is small approximation says, okay, well, this is basically unchanged. So we have our equilibrium constant expression. We have our equilibrium constant, 1.67 times 10 to the minus 7. That's equal to the hydrogen concentration squared, so that's this 2X, times the sulfur concentration, that's X, divided by, and we're going to use this approximation, 1.00 times 10 to the minus 4. So I'm going to just do a little bit of simplifying here. This is 1.67 times 10 to the minus 11 is going to equal 4x cubed. And coming up with X is 1.61 times 10 to the minus 1, 2, 3, 4. Anybody else get that number? No? What did you get?
I got 0.0000135.7.
Interesting. Well, let me double check my math. unless anybody else wants to weigh in. You got what I got? So we're really close, Ivan. Let's see. So we've got that 1.67 times 10 minus 11. I'm going to divide that by 4.
Oh yeah, I have this in the
Yeah? Okay, cool. Yeah, it could easily have been me. Okay, so that's our x. How do we check if our assumption is okay? We compare it to what we were subtracting it from. Yeah.
The 10 to the minus 4 on the bottom, should it be squared instead of just the first power?
Excellent. Yes, I screwed up on that. Thank you. This guy down here is supposed to be squared. So that changes stuff. Just by factors of 10 for the most part, but thank you. So times 1e minus 4 squared. So this over, oops, this is actually to the minus 19. Divide that by 4. Take the cube root. I'm getting 3.47 times 10 to the minus 7. Still not quite right.
Minus 19, I think it's
Minus 15.
Yeah, I got minus 15.
Yeah, it should be minus 15. What the heck did I do? Oh, I put instead of the 10 to the minus 7, I put in the 10 to the minus 11. So yeah, it was cubing it. So this is 15. Okay, let's try that again. (1.67) times 10 to the minus 15 divided by 4. Cube root of that. (7.47) times 10 to the 1, 2, 3, minus 6.
Yeah.
Answer by committee, right? There's little tiny places to make mistakes, right? That's why you need to show your work. If this was a multiple choice problem and I came up with that first answer, it may or may not be one of the choices. If it's not one of the choices, then that definitely sends me back to going, okay, I must have screwed up somewhere, right? And we can go back and look at it. And it's also nice to have a calculator that you can look back and see what you actually punched in, because I did not punch in what I listed on the screen. Okay, so is that small compared to 1 times 10 to the minus 4? We think it probably is, but we should check. 7.47 times 10 to the minus 6 divided by 1 times 10 to the minus 4. Times 100. And what do we get? Did you multiply by 100?
Oh, no. Yeah.
So 7%. Is 7% less than 5%? No. So we can't use x is small in this situation. It's the same equation. It's the same k. I know, we did all of that and we can't use it. Ah! So we're going to have to use a solver. Now, you guys totally get that I completely understand how tedious some of these problems are. Because, like, here I am. It's tedious for me up here. Okay, we can do it. So I'm just going to rewrite this so that I can see it and punch it into my calculator correctly. So this is 1 times 10 to the minus 4 minus 2x, the quantity squared. So, breaking out the solver, I've got 1.67 AE minus 7 on the one side, and I've got the quantity 2x squared times x divided by the quantity 1 AE minus 4 minus 2x, that quantity squared. So that's what my solver's telling me. You might say, well, that's not that much different. You gotta draw a line somewhere, right? What is the difference? Let's find the percent difference there. 6.78 10 to the minus 6 minus 7.47 times 10 to the minus 6 divided by 6.78 times 10 to the minus 6 times 100. That's 10%. It's a 10% difference. If you've ever gone to the store and they're having a 10% off sale, that makes a difference to you, right? So, X's small didn't work here. You can't always tell just by looking at the numbers. You look at this number, it's like, well, X is really small. Yeah, but what we were subtracting it from was pretty small too. And so it did come out really close, but it's not valid. Any questions? So just some notes. Concentrations have to be in moles per liter. Looking at a test question. Could I try to trick you by giving you concentration in some other unit? I could. What we'll see on the worksheets today is that sometimes the total volume is given and the quantities are given in moles. Well, you can't just use the moles, you have to use the concentrations because the... Could you swallow that cookie? You're making me crazy. The equilibrium constants are calculated with molarity, not with moles. If we're using partial pressures, it's got to be in atmospheres. You have to use the correct equilibrium constant. If you've got pressures, you've got to use Kp. If you've got concentrations, you have to use Kc. Those, we can convert between them, but you have to use the correct one. This is a little note here that actually can be kind of dangerous. So you can use moles or partial pressure, but only under specified circumstances. When the moles of the reactants in the equation are equal to the moles of the products. If you have 2 moles of reactants and 2 moles of products in your equation, then it's going to work out the same. But oftentimes that's not the case. So if you just always use molarity, it's fine. And then, important to note, the X is small approximation does not mean that X is 0. It just means that if we're adding or subtracting X to something else, we can ignore it. We're still going to calculate what X is. Any questions?